Section: Introduction. We, in our study, delve into the fascinating world of large vision language models, LVLMs, where innovations like LLAVA and MoE-GPT-4 have made significant strides. These models enhance a language model's ability to understand visuals by incorporating an image encoder and several layers dedicated to visual projection. It's been observed that making these models bigger and feeding them more data tends to boost their performance. For instance, InternVL has beefed up its image encoder to a whopping 6 billion parameters, and some have even pushed the backend of LVLMs to 13 billion parameters, setting new benchmarks in performance. There's even a model, IDEFICS, that's been trained with 80 billion parameters, showcasing that bigger often means better in this realm, especially when high-quality training data is available. However, the catch is that training and deploying these gigantic models requires a ton of computational power and sophisticated parallel processing techniques, making it a costly affair. This is mainly because the model needs to perform calculations with every single parameter for each piece of data it processes, a method known as the dense model approach. On the flip side, there's a more efficient method called sparse mixtures of experts, MoE, that scales up the model's capacity without needing all parameters to be active at once, which has seen success in natural language processing, NLP. A recent highlight in this space is the Mistral LLM, which incorporates MoE layers and has shown that it's possible to achieve great results with less computational demand. For example, Mistral MoE-8x7b can match the performance of Llama 2 to 70b while being more resource efficient. However, applying MoE directly to train sparse LVLMs comes with its own set of challenges, primarily because turning a large language model into a vision language model and making it sparse at the same time tends to lower its performance. After several trials, we discovered that starting off with the right initialization is key to successfully making LVLMs sparse. To tackle this, we introduced a novel three-stage training strategy we call MoE-tuning. Initially, we train a multi-layer perceptron, MLP, to adapt visual tokens for the language model. Next, we train the entire model to grasp multimodal concepts. And finally, we focus on training just the MoE layers, using the feed-forward network, FFN, weights as a starting point for the experts. This gradual approach helps the model smoothly transition from a general LVLM to a specialized sparse mixture of experts setup. Our exploration led us to create MoE-LLaVA, a new framework for LVLMs that incorporates the MoE concept and includes learnable routers to manage the flow of data. This setup allows for multiple sparse pathways, where each piece of data is handled by different experts, depending on the task at hand. By stacking these MoE encoder layers, we pave the way for a scalable, yet powerful LVLM. Our experiments have been quite promising. For instance, our MoE-LLaVA model, with only 2.2 billion sparse parameters, outperformed similar models and even the LLaVA 1.5 to 13b model in the Pope object hallucination benchmark. It also matched the performance of InternVL Chat 19b, which has about 8 times more parameters. When we scaled MoE-LLaVA to 3.6 billion parameters, it surpassed LLaVA 1.5 to 7b in several benchmarks, proving the effectiveness of our architecture and training strategy. In summary, our main contributions are the development of the MoE-tuning strategy, which allows us to adapt MoE to LVLMs effectively, and the proposal of MoE-LLaVA, a framework that significantly increases parameter count while keeping computational costs manageable. Our extensive testing shows that MoE-LLaVA holds great promise for understanding multimodal data and reducing hallucination, achieving comparable or superior performance to state-of-the-art models with a fraction of the parameters. Section Summary. In the introduction, the section discusses the advancements in large vision language models, LVLMs, highlighting the challenges and benefits of scaling up model size and dataset scale. It also introduces the concept of sparse mixtures of experts, MoE, as a way to effectively scale model capacity and presents a novel three-stage training strategy for adapting MoE to LVLMs. Additionally, it introduces MoE-LLaVA, a MoE-based sparse LVLM framework, which significantly expands the number of parameters while maintaining computational costs and demonstrates its potential for multimodal understanding and hallucination inhibition. The section also provides an overview of related work in the field of LVLMs, emphasizing the evolution of powerful LLMs and the challenges of scaling up dense visual data and models. It highlights the efforts to empower LVLMs with fine-grained image understanding capabilities and the potential of leveraging mixture of experts to make state-of-the-art LMM research more accessible. Section: MoE in Multimodal Learning. We're diving into the world of MoE and multimodal learning, where we explore a fascinating approach to handling different types of data, like images and text, together. MoE, or mixture of experts, is like a team of specialists, each good at dealing with a specific kind of information. The magic happens when a router decides which expert should handle which piece of data, making sure that the experts don't step on each other's toes. Let's talk about two types of routers, hard and soft. Hard routers are like strict managers, assigning specific tasks or data types to each expert right from the start. This method works well when the data is clearly different, like separating apples from oranges. However, it's a bit rigid since it doesn't learn or adapt over time. On the other hand, soft routers are more like savvy team leaders who learn the best way to distribute tasks among the experts dynamically, making the whole system more flexible and efficient. Our main focus is on these adaptable soft routers, especially in the context of handling both images and text together. We're particularly interested in smaller scale models that have shown promise in this area, like Eve and MoE. However, our approach, MoE-LLaVA, takes a unique path by using knowledge-rich routers to smartly distribute data, ensuring each expert can shine in its domain. Now, let's break down the architecture of MoE-LLaVA. Imagine it as a high-tech factory with several departments. First, we have a vision encoder that processes images, turning them into a sequence of visual tokens. Then, a visual projection layer and a word embedding layer transform these tokens into a format that a large language model, LLM, can understand. This LLM, equipped with attention mechanisms and neural networks, is where the magic of understanding and generating content happens. Within this model, we introduce MoE layers, where each piece of data is evaluated and sent to the top experts for processing, based on their specialties. Training MoE-LLaVA happens in 3 stages. Initially, we focus on getting the LLM to understand images by treating image tokens as if they were text. Next, we fine-tune the model with multimodal data, which includes both images and text, to enhance its understanding and control over different types of data. Finally, we replicate and initialize multiple experts to ensure that when data comes in, it's smartly distributed among them based on the router's decisions, allowing for a flexible and efficient handling of multimodal information. In essence, MoE-LLaVA is like building a super smart team where each member knows exactly what to do with the information they're given, making the whole system more powerful and capable of handling complex multimodal tasks. Section Summary. The mixture of experts, MoE, model integrates multiple submodels, or experts, using routers to assign token sets to each expert, reducing interference between different sample types. In the MoE-LLaVA architecture, a vision encoder processes input images to obtain a visual token sequence, which is then projected to a hidden size of LLM, while text undergoes a word embedding layer and is projected to obtain text tokens. The MoE-tuning involves 3 stages: adapting image tokens to LLM, tuning the LLM with multimodal instruction data, and initializing experts to process tokens and aggregate outputs based on router weights, forming a model with infinitely possible sparse pathways. Section: Objective. We aim to optimize the total loss, which is a combination of the auto-regressive loss and the auxiliary loss, with the latter being adjusted by a balancing coefficient named alpha. In simpler terms, we're trying to improve the output of our language model by focusing on 2 main areas. one that deals with generating text in a step-by-step manner and another that ensures the workload is evenly distributed across different parts of the model. For the auto-regressive loss, imagine we're given a picture and some text. Our model, MoE-LLaVA, creates a sequence of outputs, one piece at a time, until the entire sequence is generated. This sequence is a mix of positions and dimensions, symbolized by K and D, respectively. We only focus on the text part of this sequence for calculating the loss, which is a way to measure how far off our model's predictions are from the actual outcomes. Moving on to the auxiliary loss, because our model uses a setup with multiple experts, we need to make sure that all these experts share the workload evenly. To achieve this, we introduce a special kind of loss that encourages a balanced distribution of tasks among the experts. In setting up our experiments, we follow a model configuration similar to a previous version, LLaVA 1.5, using a large clip model for understanding images and a two-layer MLP, a type of neural network, with a specific activation function for processing. Our model alternates between two types of layers, with half of them being MoE layers, which are specialized for handling different tasks. The balancing coefficient alpha is set to a very small value, 0.01, to fine-tune the balance between different types of loss. We also detail how we've organized our data for training in 3 stages, starting with pre-training data from LLaVA 1.5, then collecting datasets from various sources for a robust initialization, and finally using a similar data pipeline as before for the 3rd stage. When it comes to evaluating our model's understanding of images, we test it in a zero-shot image question answering setup. This means we're checking how well our model can answer questions about images it has never seen before. Our model, being a sparse model with a soft router, is compared to previous dense models. It shows impressive image understanding capabilities, closely matching or even surpassing the performance of the state-of-the-art method on several benchmarks. Notably, our model outperforms a much larger model with fewer activated parameters, indicating its efficiency. Furthermore, we assess our model's multimodal understanding abilities using 4 benchmark toolkits designed for open-ended answers. Our results show that our model not only competes with but also exceeds the performance of larger, dense models, highlighting its effectiveness in engaging with natural language questions. Lastly, we evaluate our model's ability to generate objects consistent with a given image, using a polling-based query method. Our model demonstrates the best performance, indicating its strong capability to produce accurate and relevant objects, further proving its effectiveness with a balanced yes ratio in feedback. In summary, our model, MoE-LLaVA, showcases remarkable abilities in both understanding and generating content related to images and text, achieving this with a sophisticated balance of auto-regressive and auxiliary losses, and efficiently utilizing its components for optimal performance. Section Summary. The objective of this section is to explain the components of the total loss function, which includes the auto-regressive loss and the auxiliary loss scaled by the balancing coefficient alpha. The auto-regressive loss optimizes the output of the model through a generative loss in an auto-regressive manner, while the auxiliary loss incorporates load balancing constraints on the MoE layer to encourage experts to handle tokens in a balanced manner. The experimental setup details the model settings, data details, and evaluations, demonstrating that the sparse model MoE-LLaVA achieves comparable or even superior performance to dense models with fewer activated parameters in image understanding and object hallucination evaluations. Section: Visualization. We explored how different parts of our model, called MoE-LLaVA, work together and how they prefer handling different types of information, like text and images, when answering science questions. We found that the workload is evenly distributed among the model's experts at first. But as we dive deeper into the model, from layers 17 to 27, one expert starts to take on more work, especially handling almost all the information. In the earlier layers, 3 experts work closely together, while one expert mainly focuses on the initial layers and then steps back as we go deeper. This shows us that our model's experts have learned to divide their tasks in a smart way. When we looked at how our model deals with text and images, we noticed that the experts don't really have a favorite. They treat both types of information similarly. This is a good sign that our model is doing well in learning from both text and images at the same time. We also tracked how each piece of information, whether it's a word or part of an image, moves through the model. We found that certain experts are more likely to take charge of this information in the deeper parts of the model, while others are more active at the start. This helps us understand how our model processes information in a detailed way. Next, we tested different ways to train our model to see what works best. We tried 3 different approaches and found that starting with a specific type of training before making our model sparse, which means it can focus on specific tasks more efficiently, gives the best results. This confirms that our 3-step training strategy is effective. We also experimented with different settings within our model, like how many experts to use and how many should be active at any time. We discovered that having more experts and activating more of them at the same time improves our model's performance. However, when we played around with the model structure, we learned that making every layer sparse doesn't necessarily give better results and can even make training take longer. So, we decided to mix sparse layers with regular ones throughout the model. Lastly, we looked at how the size of the model affects its performance. Smaller models with our special sparse setup performed better than the regular dense models. This gives us valuable insights into how to scale our model effectively. In summary, our experiments and adjustments show us how to make our model work better, especially when it comes to learning from both text and images. We've learned a lot about the best ways to train our model and structure it for optimal performance.